Anyway, atomic structures. Most people, when they think of an atom, they get this little weird circular orbital thingy. And so we got to know all these little parts. Some people think it's just like planets, but it's not really. And you're going to find out some misconceptions that everybody's had. And anyway, so first off, what is an atom and how do you define it? First off, an atom is the smallest particle of an element. It retains the chemical identity. We talked about this last unit. So there are 118 elements so far that we have discovered. I doubt we're going to get over 118, and you'll see why later in the unit. The bigger they get, the more unstable they are. And an atom is made up of many things, but first we got to talk about where does the word come from, where we get all these definitions. And again, some of you are like, well, why were we talking about Greek mythology and things like that earlier? A lot of the stuff that we have learned, or names that are based on, come from the ancient Greek and the Romans. And so that's one reason why everything's based on it, and it still affects our society today. So first off, we're going to talk about Democritus. He's within this BC area, so it's not too far from, it's not too ancient. And we can go further back, but we're going to start here. So Democritus, ancient Greek, and really he did not do any scientific evidence, but he did come up with the name. No, I will not ask you anything about dates, so you don't really have to worry about the dates. This is not history class. Now, history teacher might. So, Greek philosopher Democritus. He was among the first to suggest the existence of the atoms, and it comes from the Greek word atomos. He believed that atoms were indivisible and indestructible. He believed it was the first to kind of come up with this idea that everything's made up of something very, very small. And so, we're all built up of these little teeny tiny things. This is a pretty good idea, but it was just a philosophy. Do note that he did not have any scientific evidence of this, but he was the first to suggest it. When you think indivisible and indestructible. Next guy, though, we're going to jump ahead about 2,000 years into the future. John Dalton. Now, this is where things start getting a little bit more interesting. So John Dalton we have kind of briefly talked about, but we're going to go more in depth. He has a lot of things to talk about. This is where it actually starts coming together. Dalton's atomic theory. He is the one who took the words from Democritus and actually started doing scientific experiments on it. Atoms can be subdivided. So like we just said, protons, neutrons, and electrons. In fact, believe it or not, they could actually get even smaller. They're actually made up of something called quarks, and we'll talk about it very, very shortly. Whee! Structure of atom. So one change to Dalton's atomic theory is that we just said, number one was the one that was really wrong, can be subdivided. In other words, can be divisible into subatomic particles, and y'all just said it, electrons, protons, and neutrons, and hopefully you've heard of these guys. And we're going to talk about them a little bit later, but we're going to get through the timeline here. So Dmitri Mendeleev, this is the man that you need to know. He's the man with the plan. This guy was the first guy to actually organize the periodic table. Do not get him mixed up with Gregory Mendel. Gregory Mendel was the pea plant guy. Dmitri Mendeleev was the guy who first organized the periodic table. It has been rearranged since then. And I'll even show you a picture of what his periodic table first looked like. Right now, you just need to know that he dealt with the periodic table. We're going to talk about him more later in the next unit, but I do have to bring up who he is. And yes, he does kind of look like the guy from Duck Dynasty. You know, put some camo and some sunshades on him. First organized the periodic table, but he did it by mass number. He was the first one to start categorizing these guys. Yay. Next guy, J.J. Thompson, without a P. And I had a student actually figure out a way how to remember this guy. J.J., as we call him, he did a lot of different things, but he actually was one of the more groundbreaking and starting to discovering parts of the atom. Let me go ahead and re-mention something here. They didn't know about the parts of the atom yet. So if you look at the date up there, they're just now getting to it within the 18th century. So Thomson's atomic model, they knew they were composed of some kind of charge. They knew that much, but he was the first to start giving this idea of what an atom would look like. He thought that it was like plum pudding. For you guys, fruit and yogurt, okay? Because plum pudding actually doesn't have any plums in it. It has raisins, ironically. But anyway, he kind of thought there was this big positive mass, like the yogurt, and then there was little chocolate chips or something put inside it, which were the electrons. So he knew that there was two different charges there, and basically that's where we started going around certain things. However, it's a good start. But does an atom look like that right now? No. We just showed you a picture initially, and there's one on the wall up there of how they really truly look. But it was a good start. The one problem is he could not see the nucleus. And no one's discovered the nucleus yet. But this was a good start. He knew that there was something pulling these negative charges to them, or to the center of this. But he couldn't see because of this electron cloud. It wasn't until we removed that electron cloud did we first discover that there's something underneath. It's all part of science. You've got to keep investigating. So, but remember this, plum pudding. How the person remembered this guy's name was J.J. Thompson without a P. The P was meant for plum pudding. I can't disagree with that one. That was actually pretty good. Because I'll be honest, I still forget what he does sometimes. But I do know he has to do with electrons. And I'll show you right here. Although Thompson had the positive and negative particles in the wrong place, he is credited with discovering the electrons. By the way, the white words, probably important. They're kind of like key things you might want to associate with them. So if you do go home and make flashcards with these guys, I would remember Thompson, and on the other side, electrons. And plum pudding. By the way, you know what black pudding is? It's boiled pig's blood. Yeah, I didn't know that what it was until I ate it. Yeah. Kind of tastes like pennies. Anyway, Rutherford. Okay, this guy is the other guy that they get mixed up with Thompson. Rutherford built upon the other guy's research, and they actually worked together. So Ernest Rutherford, as you can see, we're starting now getting closer to more of the modern century. But you need to know these three things about his experiment. He then was able to strip away the electron cloud and finally get to take a look at what's underneath. And what did he discover? That there was a nucleus. And he said that the nucleus was small, it is very dense, and it is also positively charged. Now keep in mind, they still have not discovered protons or neutrons yet. Only electrons, and just now the nucleus. All right. Moving on, Rutherford's atomic model. So based on experimental evidence, so the atom is mostly filled of empty space. People miss that all the time on the test. They think it's a trick question. I'll have, what is an atom mostly composed of? Protons, neutrons, or electrons, or empty space. And they're like, it can't be empty space. But yeah, most of it is empty. All positive charge, all of the positive charge and almost all of the mass is concentrated in small area in the center called the nucleus. This is why we talk about nuclear reactions. Nucleus mainly means the center. So the nucleus is composed of protons and neutrons, but they did not know that yet. They knew it was positive, but they didn't know about the neutrons, which also helps explain the problem that Dmitri Mendeleev had when he started organizing the periodic table. You can have elements but have different mass, elements that are the same but have different mass, and we'll talk about how that mass changes. Electrons are distributed around the nucleus and occupy most of the volume. So when they say it's mostly composed of empty space, that's because the electrons are nowhere close to the center of the nucleus. So there's a lot of gap in between, is what they're saying. But the electrons are moving so fast that they form this nice electron cloud, which kind of looks like it fills space, but it really doesn't. It's one of those optical illusions. His model was called the nuclear model. And this is where, you know, nucleus, nuclear, all that started sticking. Science. All right, next guy, Niels Bohr. What did he do? Bohr model! So anyway, Bohr's model, Niels Bohr discovered the energy levels of the electrons. And that really should be written in white because that is actually the most important thing he did. He did come up with the idea of the orbit kind of thing, like planets around the sun. It is a good idea, but it does not do that. But it's a good way to start out, and actually we still use his model sometimes. It's a great model. It really is. It does help you visualize and get an idea of how many electrons are in what level. The levels are extremely important. The further you go out, the more electrons you can hold. If you're closer to the center, you can't hold very many because it's a very small circle. That's also how we get the organization of the levels on our periodic table. But that's what it looks like. We'll see more of these things a little bit later. That gets a little bit more complicated the bigger they get, but we found a way to actually make it easier. I mean, I can go ahead and tell you that that is going to be sodium. How do I know that that is sodium? Well, it has 11 protons, and we'll talk about how we actually get all that. Also, the modern wave model of the atom started getting us ideas there, because you're like, well, how can we see these things? Well, we really can't see them. Next guy, Henry Moseley. We'll talk more about him later too. Just like Mendeleev, he actually reorganized Mendeleev's periodic table. He reorganized it because Mendeleev did it by atomic mass. This guy did it by atomic number. And we'll talk about how those two are very, very important later on. He didn't really have to rearrange much about the other guy, but, you know, again, next unit. Erwin Schrödinger. Schrödinger, sorry, but we like to say Schrödinger in the South. So this guy is actually, you've heard of him if you actually watch The Big Bang Theory. If you watch that little show, they talk about Schrödinger's cat. But this is getting now more into wave theory, and we're going to kind of start, this is where I start pulling back a little bit, because this gets more into the physics, and we don't really have to go too much into that. But I will tell you, it is kind of neat, because this helps us figure out how we are actually able to see colors and things like that. And yeah, you'll do a lab a little bit later where you set things on fire and see different colors pop up. As long as you don't burn the building down, we'll be fine. Whee! And last but not least, we're going to talk about Louis de Broglie. Broglie? I always call him Broccoli. This guy also gets more into the wave. Again, this is, I'm pulling back a little bit because when we start talking about wave theory and things like that, about how we're able to see certain colors when we actually excite electrons, it goes back to this guy too. He discovered the wave nature of electrons and suggests that all matter have wave properties. He won the 1929, I'm getting ahead of myself, Nobel Prize for Physics, and it was a big game changer. And we'll do some of the experiments that are very close to what he has, shown us. But wave nature is a very big thing, and actually one of my favorites, but too bad we don't get to do equations in here with it. So anyway, you get the idea of an atom that we have here. They put it more like a Bohr's model in this one, but you can count how many positively charged things, and then you see things that don't have any charge. Those are the neutrons. The reason why they're called neutrons is because they're neutral, not because some people think they have a negative charge because it begins with an N. Neutrons mean neutral. That's why. Protons have a positive charge and electrons have a negative charge. This you should know. You're like, okay, this is familiar. I'm getting there. All right, so now we're actually going to start going into a little bit more important things. All right, about atoms. There are presently 118 elements, thus 118 different kind of atoms. Each one has their own different properties. You can also take these guys, combine them with different ratios, and form tremendous numbers of compounds. And the electrons move around a space around the nucleus called the electron cloud. That is their home. It makes sense. The reason why they call it a cloud is that these guys are moving so fast, it looks like a blur. Imagine that. So, what is that? Electrons have a negative charge. This is where we start getting to how bonds work and things like that. These electrons are very, very important with that. The electron's mass is much less than that of neutrons and protons. They have to be, because one, they're moving that fast. And they also, we like to depict them as a lot smaller than they really are. So electrons are small, protons and neutrons are almost the same size. One's a little bit bigger than the other. That's where I get to mind-blowing people. Because nobody ever tells you. Here's a joke. Oh my gosh, I lost a neutron. Don't worry, you can get a new one. Free of charge. All right. So this is the picture I kind of have very similar in the back of the room here. Obviously you can't see it, it's very small. But this one's a little bit bigger. I kind of like it. But let me zoom in. And this is not going to be on the test, but I want to show you how much more crazier it can get. Inside protons and neutrons, there are quarks. And depending on how this quark spins, up or down, actually makes what a proton and neutron really is what it is. You'll notice, though, also the quarks are about the same size of an electron, which is kind of interesting. They're about the same size. Not really, but close. But that gives you an idea how much crazier it can get. There's one little quick video I'm going to show you. Again, this is just to give you fill in the gaps of the mysteries of where we think some of these things come from. Again, theory-based. And so now we actually get to the size and the idea here. Now earlier we said that the atom is mostly composed of empty space. This does not give a very good representation of it, but it gives you a good idea of what they mean. They mean by volume of the whole thing. In other words, from the center to the most outermost electron. They're talking about that space in between is very, very empty. So if we were to put this to a perspective, if I had one of you hold one baseball, and another hold another baseball, one of you hold a baseball and the other hold a basketball. Basketball representing the nucleus and the baseball representing the electron. I would have to get y'all to stand 2 football fields away from each other just to get an idea of how much space there is in an atom. And that's a lot of space. And that ratio is almost a little bit true with the size of the proton and the electron. Now you also got to think, that's just the radius. That's not the diameter. Whee! So this guy is actually the most important thing to actually sum up a lot of the things. Put it all on a chart so you can actually visualize it a little bit better. First thing, every single one of these guys have a different charge. They also have a different mass. However, 2 are located in the same spot, in the creamy filling, the nucleus. But if you actually take a look at their mass, that's where the interesting thing happens. So what's interesting enough is that we can't actually find the mass of each one of these guys, but if you actually take a look at the top number in the mass column, that's how much it is in grams. You might think that's a lot, but negative 28, that's in scientific notation, that means you move that decimal 28 times to the left. So which one's easier to read though, the top number in the mass column or the one right below it in AMU? I'd say the AMU because it's a little bit easier to memorize instead of 9.11. I mean, which one would you rather memorize for a test? I'd do the AMU. I mean, if you want to make it easy on yourself. If I told y'all to memorize in grams each one, y'all would be, have that deer in the headlight look. Now, I will give you an idea here. AMU is a short way. It means atomic mass unit. That is actually very, very important. This is how we're going to measure the units so far when we look at these guys. So when we take the mass of an element, it's going to be an AMU so far. It will change when we get to stoichiometry. But anyway, first off, let me ask you this. Does an electron have mass? It's not a trick question. It looks like a trick question, but it's not. It does have mass because that is actually the mass. The approximately 0 AMU. Now, if I bluntly said 0 AMU, that would be no mass at all. But it's approximately, which means it's got a little bit, but not enough to make it a whole AMU. Okay? It's kind of like you got like 1 penny versus, these guys are a whole dollar. Now, 1 penny is not going to make much of a difference. Actually, to technically make it that same way, I would have to say 1,000th of a penny to actually make it within a certain kind of ratio here. So it's not even close, maybe even 10,000th of a penny. It does have mass, but it's very, very low, which is good, though, because this is one reason why this guy zips around the nucleus all the time, because he has hardly any mass. These 2 guys have a very similar mass, but one's a little bit heavier than the other guy. Which one's the heaviest? Look very closely. The neutron. Even though they have the same AMU, this one, if you compare the 2, this one's just a little bit bigger. Where do neutrons come from? We talked about protons and we talked about electrons, but nobody knows actually where neutrons come from. Here's the most interesting thing here. They have a 0 charge, right? This has a negative charge, positive charge. -1, +1, what's the value there? 0. 0 plus 1. You see where I'm going with this? When an electron actually gets to finally touch a proton, they become a neutron. No one ever tells anyone that. They just assume you already know. And let me go ahead and tell you, there are people in college, if you go up and ask them that, they don't know that. It's really kind of mind-blowing. They skip over it for some reason. And if you don't believe me, go ahead and add this mass, put it in parentheses obviously, plus this mass, you'll get this number. That's actually how you know. So that's actually how we get different kind of neutrons sometimes. Occasionally, an electron can finally get to a proton. They're attracted to each other because they're opposite charges. So eventually, they might actually get together, but they come out to be a neutron. The mass comes together. And it's kind of interesting how that actually works out. This is one reason why we get different kind of mass numbers. Do keep in mind, though, that the mass of an electron does not affect the mass of an atom. That's why it says 0 AMU up there. That's important. So you can throw in tons and tons of electrons. It's not going to affect the mass of the whole atom very much. However, when it comes to protons and neutrons, it will. Now, this is the interesting part of the unit. So this is not written in the notes, so you might want to write this on the side. Okay? I really should add in another column here because there's something I want you to kind of get a kind of like a metaphor or a synonym with what their jobs are, because we didn't talk about their jobs at all, and they all have a different job. Once you know their job, you kind of get an idea of what is possible and what's not possible. All right, let's start with the most important one, the proton. This is the identification. I already talked about that, so I would say the number of protons identifies the element. Nothing else does it, only the proton. You change the protons, you change the identification. And you'll notice each element up there has a certain atomic number, therefore a certain number of protons. The more you add, the more unstable you get. It's just like building a structure. We can only build it so high until something happens.
This category is called jobs or something, or what it does?
I would say, yeah, the jobs. Let's go with jobs, or its purpose. So this just identifies it. It does also cause attraction for electrons to come in, obviously, but it's the most important, in my opinion, because it's the identity. That's how we identify them. Let's go up to the next one that I think is the next best important. They're all important, but electrons. What is the job of the electron? Electrons are all about the bonding. That's how we're able to form compounds. They bond. That basically the number of electrons tell you how many bonds they can form. So it's their function or their purpose is bonding. How many electrons are in a bond? Well, two. It takes two to tango. You can make stronger bonds by double bonds and triple bonds, but we'll get into that a little bit later, not in this unit. We'll get in that next unit. Actually get to see structures. So identification, bonding. Last but not least, and it's not like they don't have a purpose because they do, but honestly neutrons, they help balance out the nucleus, but the main thing I want you to know about them is their dead weight. That's it. Because they don't have a charge, they really don't do a function. But they do give the mass to the atom. They do contribute to the mass, a large quantity of it. Protons do too, but you can have a lot of neutrons, and this is where we end up getting our isotopes. Let's also say stability, because that's actually important too. Dead weight and stability. I like to call them, here's my other name for them, the fat of the molecule. So again, protons, they have to do with identification. Electrons have to do with bonding. Neutrons have to do with weight. And when I say weight, I mean W-E-I-G-H-T, not the other weight. But they have to do with weight and stability.